Okay, so now we're going to look at compounding periods. So many investments don't calculate interest just at the end of the year, they calculate interest more frequently than that. Most common is monthly, but there are other interest rate compounding periods as well. So what this means is that even though interest rate is always given to us in a year, it'll be like 5% per year, how often the interest is added to the account is more often than that. So it could be instead of yearly, it could be monthly or quarterly or semi-annually, weekly, biweekly, daily. There's other modes as well, but those are some of the common ones that we'll start by going over here. So in order to work with these different compounding periods, we have to understand how many occurrences of a monthly compounding period there are in a year, since so much of our information is going to be given to us in years itself. So compounding period is the interval of time between interest calculations. So if we have a monthly compounding period, that means that we have 12 occurrences per year, which makes sense. There's 12 months in a year. Quarterly means that it's 4 times a year, once every quarter. Another way to think of this is it's once every 3 months. Semi-annually means every half year, which means it's twice per year. Weekly, so that's every week. Now, we're going to estimate this one a little bit. We're going to say 52. There are 52 weeks in a year, but there's 52 weeks and then like I think one other day, depending if it's a leap year and stuff like that. So over the course of like 10 years, not every year is going to have 52 weeks exactly. Some years will have a 53rd, just because of if we say, oh, every week counts on a Monday or something like that. But we'll just always leave it as 52. We're going to skip by that. We're going to ignore leap years the entire time. We also assume every month is like 30 days, but we won't do that too often. Biweekly, that means every other week. So every other week would mean that there's half as many compounds in a year, so 26. And daily, well, that's every day. So that's 365 days in a year. And of course, we're ignoring leap years. Okay. So with that in mind, let's look at how we actually use the compounding period to modify the question to get the answer. So we're going to start with a very simple, straightforward example. So Billy invests $1,000 at 5% per year, compounded quarterly. So remember, that means it's 4 times per year. Okay. How much is it worth after 5 years? Okay. So our present value, which is the value at the beginning of the investment, is $1,000. And the compounding period doesn't affect that, but it does affect the other two values. So our interest rate, remember, is our interest rate per compounding period. It says 5% per year. That doesn't mean every quarter they get 5% more money. That means over the course of the year it would be 5%. So that means we have to divide our 5% up into each one. So we can do this calculation. So our 5% divided by how many quarters there are in a year. And we can compute this one nicely. 0.0125. We get an okay decimal. Sometimes we'll leave it in a fraction. We'll see that in a little bit. Okay. So we also have our n value. Remember, n is the number of times interest calculated. So we have a total of 5 years. 5 years. But interest isn't calculated 5 times. It's calculated every quarter of a year. So that means we have 4 compounds per year, which means we have a total of 20. We multiply them together, we have 20 interest calculations of this smaller interest rate. So interest rates are almost always communicated in a per year based, even if the compounding period is something else. Okay, that's just to help keep the clarity of communication a little easier. It's a little easier to compare interest rates, But as you'll see in some of the practice questions, changing the compound period does affect things more than you might suspect. All right, so let's do this calculation now. So we want to know the future value. It's going to be the present value, 1 plus I, 0.0125, the power of n, 20. And once again, make sure you're very careful plugging this into your calculator. You want to make sure you got brackets in there. 1,000 times open bracket, 1 plus 0.0125, close bracket, to the power of 20 equals $1,282 and a little bit of rounding, 4 cents. Okay. Let's take a look at our next example now. So you have $5,000 owed on a credit card. The interest rate on your on your credit card is 24% per year, compounded monthly. Okay, that is a realistic interest rate on a credit card. Credit cards have insanely high interest rates. Credit cards are not meant to be used as loans of money. People use them like that because they don't understand interest or they just make poor financial decisions. Please never be that person. Okay? Never owe money on your credit card. Okay. So, how much would you owe after 4 years? So, currently, present value, owe $5,000. Our interest rate is 24%, 0.24 as a decimal. Compounded monthly, so that's 12 times per year. So over 12, and that actually works out to be a nice decimal again, 0.02. And, well, we have 4 years. And we have our compounding period is 12 times per year. So that's a total of 48 compounds, 48 interest calculations. Okay, so let's figure what the future value is. What would you owe if you didn't pay your credit card bill for 4 years? $5,000 times 1 plus 0.02 to the power of 48. And we can use our calculators for that. We get $12,935.35. That is a lot of extra money owed. And this is why it's a very bad idea to owe money to your credit card, because the interest rates are insane. You can, with credit cards, you can always avoid the interest rate. You never pay interest if you fully pay your credit card bill when you receive it. So it's a due date, and if you pay it before then, you don't owe anything extra. If you buy $100 jeans, that's really expensive, but if you buy $100 jeans and you get a credit card bill for $100 and you pay the credit card company the $100, you just pay them $100. That's the end of the story. If you get the credit card bill for $100 and you don't pay it and you wait a month, 2 months, then all of a sudden you're going to owe them $105, $106, and it doesn't feel like you owe them that much extra, but it grows and grows faster and faster because as the balance grows, the higher that multiplication gets and adds to the bill over and over and over again. And that's how people get in trouble with credit cards. Okay. All right, let's do another one. You want to have $1 million for retirement. I hate to break it to you, but $1 million sounds like a lot of money for retirement, but it's not. Retirement is very expensive because we all live so long these days. But part of it is $1 million. Okay. If you find an investment that earns 9% per year, compounded weekly. So we got our 9% here, compounded weekly. Let's just remember that's 52 times per year. How much would you need to invest when you're 16 in order to achieve your goal at 65? First of all, it's asking how much we need to invest earlier, so it's asking me to find the present value. And it's telling us the future value of $1 million. Okay. So let's go through and try to find the rest of the information here. So our future value we have, we want to find present value. Interest rate, well, that's going to be 9% over 52. And if you punch it in your calculator, you get, I don't know about your calculator, but mine gives me like scientific notation that's really awkward to work with. So in this situation, because I'm getting a really small decimal, because each week's interest rate is really low, but over 52 weeks it goes up to 9%. I'm just going to leave it like this for now. We'll plug it in our calculators like this when we do our calculation. Lastly, we want to know n. So n is the number of years times our our compounding periods per year. So it's going to be times 52 per year. But how many years is it between 65 and 16? I need to do some subtraction there. 65 minus 16, well, that's 49 years. 49 years times 52 compounds per year. That is $2,392. Okay, let's write this one out. So we know the future value is $1 million. Another 0. Want to know how much the present needs to be. So 1 plus 0.09 over 52 to the power of 2,392. So once again, make sure you're very careful with your brackets here. And I'm just going to calculate the number, get this number on the right side first, and then it'll be easier to rearrange it from there. 1 plus 0.09 divided by 52, close bracket. I don't think I ever opened a bracket here, so I'm going to go back and redo that. To the power of 2,392 equals, get a big number, $1 million. It's equal to our present value times 62.578, etc. And once again, I'm going to leave that in my calculator and just do 1 million. Make sure I count that I have 6 zeros. Divide by answer. We get a present value of $15,979.93. Okay. So if you think about that for a second, so if we could earn 9% per year, which is high, but it's not super high. But most of you are around 16. If you had $16,000, which is a lot of money when you're 16, and you invested it now, it could be worth $1 million when you're 65. That's a lot. All right. That's it for now.